A block of mass m1 slides on a horizontal frictionless surface. With the velocity of v1, it collides with an ideal massless. That's good because that way when the group moves, the mass of the spring doesn't really factor into the kinetic energy. Collides with an ideal massless spring, which is attached to a block of mass m2, which is initially at rest. The spring has a spring constant of k, which is 175 newtons per meter. What is the common speed, vc, that the two masses in spring will be moving when the spring is maximally compressed? Okay, so the idea here is block 1 collides with block 2. They then come together and then are moving together at some point with a fully compressed spring, maximally compressed. So you can think of the spring, it moves this way once hit, and then it compresses to a maximum amount of compression, which is this point right here. At which point, M1 and M2 are moving together. So M1 comes, hits the spring, starts compressing it, and then M1 and M2 move together. And at the point where the spring is most compressed, there is no relative motion between 1 and 2. So what we're going to do is we're going to look at this as a conservation of momentum issue. So we can say momentum 1 plus momentum 2, 1, 2, equals momentum 1, 2, where this is going to be a completely inelastic collision. So it basically means starts as two objects and then continues off as one object. But that one object is only one object for a very small, brief period of time. But that brief period of time is when the spring is maximally compressed. So that's the one we're looking at, which is convenient. Okay, so we know that, boom, 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 we're going to look at this. The mass 2 is initially at rest. So wait a second. Initially at rest. So we have the momentum of 2 equals 0. So we have mass 1 v1 equals mass 1, 2 v1, 2. And what is the common speed? So this is vc. Vc is v1, 2. So solving for v1, 2, we get mass 1 v1 over mass 1, 2. Mass 1, 2 is just the combined mass. So we'll say mass 1 v1 over mass 1 plus mass 2. There we go. So mass 1 v1, mass 1 plus mass 2. There we go. Excellent. If mass 1 is 1.5, mass 2 is 6 kilograms, and the common velocity at the maximum spring compression is 0.4 meters per second, what is delta x max, the maximum spring compression? So we've basically modeled this as an inelastic collision, but that's not entirely fair. So with an inelastic collision, you have two masses come together and then they leave as one. Well, these are only going to be one combined object for a moment in time, maximum compression. And so we can look at this also as an inelastic collision because there's no energy loss to deformation. It's an ideal spring, so it means that you're not going to have energy loss due to friction or that sort of thing. And they're all moving on a frictionless surface here, so it means we're not losing energy due to the surface. So we can do a conservation of energy. I'm going to take a look at that real quick. So we have energy kinetic. I'm going to say 1 initial plus energy kinetic 2 initial. I'm going to leave off energy potential because it's one dimensional. They're not moving up and down. This is all horizontal. Energy potential. Okay, I'm going to do energy potential of the spring equals, and it'll be initial energy. We're going to go kinetic 1 final plus energy kinetic 2 final plus energy potential spring final. Now there's a lot of extra terms in here, but I kind of like the idea of everything on the left, everything on the right. So this is everything we start with over here. This is everything we end with over here. Now you might be like, well, you moved the, I re-separated the energy kinetics apart. I don't need to. We'll see later that we could put them the same. I could have put them together, but leaving them apart is okay too. Up here, when we had P12, we could have written this as P1 plus P2 final. This is then with mass 1 V1, these are both final, plus mass 2 V2, but V1 and V2 are the same, so then we get mass 1 plus mass 2 times V common. So even though I wrote this as momentum 1, 2 together, I could have separated them. And that's the same thing I did down here. I just separated the two kinetic energies, even though effectively they're one object. This just helps keep it clear in my mind what's going on. Okay. So energy kinetic initial, that is going to be 1/2 mv squared from our initial motion. The second block, m2, initially at rest. So energy, 1/2 mv squared, is going to be 0. Spring is initially uncompressed, so that's going to be 0. These two are going to be common, so we'll write those out, but there will be something there. And then this will have some sort of delta x involved, which will give it spring. Okay. So, writing this out, the initial 1/2, let's say, I'm going to say m1 v1 squared, even though I know those values, equals, and I'm going to say 1/2 m1 v1, this is initial, final squared, plus 1/2 m2 v2 final squared, plus 1/2 k delta x squared. And this is just the formula for a spring, the energy due to a compressed spring. So, which you should know. So now we're going to combine some things real quick. So this is 1/2. Actually, I'm just going to get rid of all the 1/2s because they can all cancel. We know that this and this are equal, so it's going to be mass 1 plus mass 2 times, and they use the term V common, which I'm going to use now, V common squared, plus K delta X squared. We know what K is. And then we have mass 1 V1 squared. So we know, I think, everything here. Yep, because we know what the we know what V common is. It's this, which we'll put it in a second. We know they give us the value right there, okay. Do we have V1? We don't have V1, but I think we can find it based on this. So I'm going to take that equation and rearrange it. Everything's so messy now, so messy. That's kind of how my thought process works. So we have V common times mass 1 plus mass 2 all over mass 1 equals V1, okay? So then, what we're looking for then is just delta x squared. So let's try this out. Let's plug this in. So we have V common, V common, mass 1, there we go, times V1 squared. So we V common squared times mass 1 plus mass 2. Let's just calculate that out. That might be easier. I'm going to calculate that out. That way I don't have to worry about keeping a million variables and then square them. Pull up the calculator. Clickety-clack. Clear. Okay, so now, looking at this, we know that V common is 0.4. And we multiply it by 1.5 plus 6, which is 7.5. And we're going to divide by 1.5, which is the mass 1. So that's 2 meters per second. Oop, write that down. Blue equals 2 meters per second. Okay, so now delta x squared equals mass 1 V1 squared minus mass 1 plus mass 2 times V common squared all over K, which looks like an R. There we go. So we have 1.5 times 2 squared minus 1.5 plus 6, which is 7.5, times 0.4 squared all over, was it 175? 175. And this will give us delta x squared, which we'll take the square root of. Therefore, delta x equals, we can do this in the calculator. So we have 1.5 times 2 squared. I know I could just put in 4. minus, let's do parentheses, 7.5, that's 1.5 plus 6, times 0.4 squared, parentheses, divided by 175, second square root, second answer. This gives us delta x, 0.166. 0.166. And I think that's going to be in meters. So, about that far. So, right here. This is going to be the answer. Okay, we did a lot of stuff there. This is like, you only have 2 to 3 minutes to do these problems. So this is actually a lot of work, a lot of crazy work, kind of off the wall for, just one problem, which highlights the point of why it's so important to get the easy problems correct, because you want to get as many points on the easy problems, that way you can afford to miss a couple on the more difficult. Backtrack, looking at what we did. So for this part, second part, we were given all this data and we're trying to find delta x. We look at this as like, all right, we can do an energy balance here because we don't have any energy lost anywhere. Therefore, the energy is going to be the same on the left and same on the right. All the energy on the left is going to come from M1 moving, but the energy on the right is going to be from M1 and M2 moving, which are moving together, and a compressed spring. And we want to find out how much that energy is in that spring, and that way we can convert that energy into a compression. So we had our equation out, but we didn't know what V1 was. Well, if we look at our first problem, they gave us Vc, the common velocity, and it had V1 involved, so we could backtrack and find out what V1 was. It gave us 2 meters per second, which made sense. M1 was moving faster than after it collided, so that seems reasonable. We found that out, we plugged things out, we rearranged everything, and we found delta x squared, square root that, and that gives us delta x. So that's how we found the compression spring. Kind of a tough problem. It's kind of one of those things where you have a whole bunch of equations, throw it in a box, you shake it up, and you look at it, and if it's what you want, it's good. If it's not, you do some more shaking until what you want kind of just falls out. Not the most pre-planned attack, but sometimes you walk into these things, middle of the woods, have no idea what's going on, and you just do your best. All right, I hope that helped. I will see you guys next time.